Hi, my name is Azim Polat, and this is my screencast for Operating Systems Project 2 Custom Memory Manager in C++. We'll start with the header file, memorymanager.h. This contains the class declaration, internal data structures, and public function prototypes. Here are the standard headers. And here we define max word count limit. This caps how many words we can allocate in total to prevent oversized memory usage. The two allocation strategy functions are declared globally, best fit and worst fit. Note that these are not part of the memory manager class. Here's our class declaration. The class is called memory manager. For the core structures, we define a struct called memory block that has an offset, a word count, and a bool is whole flag. This represents either a whole or an allocated region. I use the list data structure to store memory blocks and track both wholes and allocations. Here is a list called memory blocks to hold all memory segments in order, and a map called active allocations to track pointers and look up the original memory block when freeing. These are our private helper functions. Design follows what the lecture called a holistic approach. In Module 5, we maintain a linked list of blocks where wholes and used regions are stored together, but marked with a flag. This lets us allocate free memory efficiently. Here is the public interface of Memory Manager class. We have a constructor and a destructor. Since this class directly manages raw memory, copying it could lead to shallow copies or double freeze, so we delete the copy constructor and assignment operator. Then we have all our main methods declared: initialize, shutdown, allocate, and free, along with set allocator, and there are also several getters. Let's walk through all of these in the implementation file next. memorymanager.cpp, starting with best fit and worst fit. Both functions take a whole list generated by getList. Each whole is represented as a pair, offset, and size. Best fit finds the smallest whole that can fit the requested size. The list is formatted like count, offset 1, size 1. We loop through and return the offset of the best fitting whole. If nothing fits, return -1. Worst fit is the same as best fit, but picks the largest whole that fits. Here is the constructor. It takes in the word size and an allocator function. We store both and set everything else to safe defaults. The destructor just calls shutdown to release memory and clear internal state. Initialize is called before we can allocate anything. If memory was already set up, we call shutdown to clean up. Then we allocate a new block with new and insert one large hole. Shutdown deletes the raw memory, clears the whole and allocation list, and resets all tracking variables back to 0. Allocate is the heart of the memory manager. First, we convert the requested size into words. Then we call getList and feed it into the current allocator. If we get a valid offset back, we find the whole, and depending on leftover size, either split it or use all of it. The pointer is stored in the map, so free can find it later. Free looks up the pointer in the map. If it's found, we mark the block as a whole, then try to merge it with any adjacent holes. Finally, we erase it from the map. Set allocator lets us switch allocator strategies at runtime. GetList returns a dynamically allocated array listing all holes used by the allocator functions for hole selection. Format is count, offset 1, size 1, offset 2, size 2, etc. GetBitMap returns a byte array where each bit represents a word. The first 2 bytes store the size in little endian format. 0 means the word is free, 1 means it's allocated. And getWordSize, a simple getter, just returns the word size used for alignment in bytes. GetMemoryStart returns the base pointer to the allocated memory block. GetMemoryLimit returns total size of memory in bytes, word size times total number of words. DumpMemoryMap creates a string of all whole offsets and sizes. It uses POSIX open, write, and close functions to write to a file. Returns 0 on success or -1 on failure. Find block by offset searches through memory blocks to find a block that starts at a given offset, takes in a word offset, and returns the iterator pointing to the block at that position. Merge adjacent holes takes an iterator to a whole block and checks its neighbors. If the blocks before or after are also holes, we merge them into one big hole to reduce fragmentation and to keep the list compact. Finally, calculate bitmap size bytes. Calculates how many bytes the bitmap needs to store word level info. Each bit maps to 1 word, so we divide total words by 8 and round up. Now let's do a quick demo of all tests passing. As we can see, all heap blocks were freed and no memory leaks detected. That wraps up my screencast for Project 2. Thank you for watching.